Here we're going to see another way to solve the system of equations. And this method is going to be based on the Jacobi method. It's a slight modification of the Jacobi method. The idea is very simple, but at the same time it's effective as well. So the idea is the following. When the Jacobi method is implemented, so this is the Jacobi method here, some of the values, some of these values here, we have to solve where this is implemented just starting from some initial guess, and we get the u1 up to u2, un, and some of them, of course, they are evaluated before the others. For example, this u1 is evaluated before the u2, and the un is going to be the last one in the iteration. So in the Gauss-Seidel method, we use these updated values as soon as they are calculated. So what is that? The idea is very simple. So that's why this is the Jacobi method, the one we do have here, and the Gauss-Seidel method. So that's why I'm going to change that with the Gauss-Seidel method is the following. So basically here, for example, we apply the Jacobi method to calculate in the new iteration the u1. So when calculating the u2 in this iteration, we are going to use the u1, not the one from the previous iteration, but the one that we have just obtained. Thus here we're going to replace that one with the new one that we have obtained. And so on and so forth. For example, in this last one, we're going to use all the un values that we have obtained, which are all these ones, all the others, but this one, but this and this one as well. So we're going to use all the values that we have obtained here. So this is basically the Gauss-Seidel method. And on the following, we're going to define some matrices so that we can write the Gauss-Seidel method in a more short way. That's basically, we have shortcuts to define this Gauss-Seidel method that can be quite interesting, can be useful at some point as well. But the main idea is the one we have just described. So in order to write them in a short way, we're going to define different matrices. So here we have the M matrix here. We are going to write this M matrix as the sum of a diagonal matrix first, which is this one, which is just the element we do have in the diagonal. These are the ones, and all the rest elements are 0. So this is the diagonal matrix, and this is the N matrix, plus some upper triangular matrix we are going to call T, which has elements just in the upper diagonal or with zeros in the diagonal. So are those elements here, these elements here, are those belonging to this T matrix. So that's going to be the T matrix, plus another one, which is going to be a lower triangular matrix, again with zeros in the diagonal, which are these elements here, those elements which are below the main diagonal here. So these elements here. We are going to split, therefore, our M matrix in these 3 different matrices. So I can use this representation in order to write this M matrix in the Jacobi method, in order to write the Jacobi method, to make it more elegant, let's say. We already said that we can write in a short way all the equations in the Jacobi method in this way. So we can use this matrix representation in order to write this expression using this matrix, for example. We do have this 1 over m, that's coming from the inverse of this D matrix, but the inversion of this matrix, as you can see, is just the inverse of the elements on the diagonal. It's very straightforward. Then you have this Q vector, this is the Q vector, minus, then you have, this is basically T matrix times U, and this is the L matrix times U. So we can write it in this way. We can write the Jacobi method in this way. And actually it can be useful to see the Jacobi method representation in terms of these matrices that we have just defined. And we're going to use in the following these matrices that we have defined in order to express the Gauss-Seidel method as well. So that's what we are going to do just now. In the Gauss-Seidel method, we use again the updated values as soon as they are calculated. So again, this is the short way of writing this, the Jacobi method. And in the Gauss-Seidel method, you can see that whenever applying all the u vectors we do have here, for example, where j is going from 1 to n minus 1, so this is the expression that we do have in order to have in this j plus 1 iteration in order to have the expression for the un, but all the previous ones, so all the elements going from 1 to n minus 1, they have already been calculated. So this one, we are substituting these elements here, these u elements, but those that have been calculated in this iteration, in this j plus 1 iteration. So basically, in the Gauss-Seidel method, we are substituting this one, coming from the Jacobi method, with those values obtained in the j plus 1 iteration. So that's the difference, again, writing this short way from the Jacobi method, said before, we described before, and the Gauss-Seidel method. And we can use this matrix representation we have just seen here in order to write this Gauss-Seidel representation using the DLT matrices we have just defined. Again, we have this u vector is coming from this one, so the u vector obtained in the j plus 1 iteration can be written as the inverse of the D matrix, which is represented by, is coming from this, associated this 1 over mnn times this q vector minus that will correspond to, this correspond to the lower trigonal matrix times the u vector calculated in the j plus 1 iteration minus that will be the T matrix, but in this case, times the U vector, in this case, the one calculated in the G iteration, because they have not obtained yet in this iteration, in the J plus 1 iteration. So we can write this, the Gauss-Seidel representation, in this way as well. And actually, what we can do here, we can bring that one to the other side, and we can have a matrix representation, right, in the short way, that before U at the j plus 1 iteration.